Our next speaker is Anabel Ovide González. Anabel Ovide González earned her bachelor degree in computer engineering from Technical University of Madrid in Spain. Following this, she pursued a master's degree in computer science with a specialization in quantum computing at University of Tartu, Estonia. Anabel further expanded her expertise at Ulm University, Germany, where she worked as an assistant researcher. There, she contributed to experimental research in laboratory focused on nitrogen vacancy centers, gaining hands-on experience with one of the leading physical implementations of quantum technologies. Building on these experiences, Anabel began her doctoral studies at the Technical University of Valencia, Spain, where she is currently researching the optimization of quantum programs for application in quantum networks. Her work is particularly centered on the compilation of quantum programs tailored for ion trap technologies, which is a leading platform in quantum computing. So with this, I would like to invite Anabel for her talk on quantum internet and compilation of quantum programs. Anabel, the floor is yours.
Hi, thank you for the introduction. I'm going to share my screen.
Yeah, please.
Okay.
You share the screen? Yeah, I think, yeah, now it's visible. Yeah. Thank you.
Okay.
Please continue.
Can you also see my pointer? Like my mouse, in case I'm like...
Yes,
okay.
Yes.
So I'm Anabel, as he has said. I'm a PhD student in the Technical University in Valencia in Spain, and I'm going to talk about my PhD research that is focusing in the optimization of quantum programs, more focusing into the compilation phase of it. I'm working in the KIA project, that is the Quantum Internet Alliance. So what we are doing is the first quantum internet prototype in Europe. And we are a lot of different partners across all Europe. Here are some of them. And my PhD is funding from this project, basically. So what is quantum internet? The structure of it is very similar to the classical one, in where we have the different clients. We also have servers, routers, and links. The main difference is that all of these components will have a classical part and a quantum one. And my research is focused in the servers that we call M nodes or quantum nodes. The applications that are usually run in this quantum internet are the quantum key distribution, QKD, distributed quantum computing, secure quantum computing in the cloud, also blind quantum computing, anonymous voting, and this kind of application that are more focused onto the distribution, the quantum computing distribution, or more into protocols for secure information exchange. These applications are going to be split into different programs, and these programs are going to be shared, are going to be in the different nodes, like each program for a different node. All of these programs are composed by classical and quantum code. In this way, we can execute the different programs in a parallel way, and they will communicate to each other. So the nodes are also composed by a quantum part that will be the QPU, and for a classical one, that it will be a classical processor. In the quantum part, there will happen the quantum operations, such as the entanglements, the quantum gates, and the measurements. And in the classical, there will be the classical communication through the different servers and also classical processing. So basically, what a quantum node is a quantum computer, but with an external interface, so we can communicate with another quantum nodes. This external communication are going to be via quantum channel and a classical one. In the quantum channel, we are not going to do anything else more than the quantum entanglements. And for the classical channel, we are going to share classical information like bits. Then we cannot just execute the programs into the nodes, since its quantum hardware is going to have a different limitation. So we have to adapt these quantum programs to the different hardware. via the mapping procedure. For example, in the superconducting, we have the restriction that the qubits that want to interact with each other need to be in an adjacent position. And I want to explain now to you the mapping procedure with an example, because I think it's easier to see in an example visually than just if I explain all the theory. But you have to consider that the example is going to be in a superconducting technology, and in each hardware technology, the constraints will be different. And also in this mapping procedure, we are going to try to optimize the quantum algorithm, trying to reduce the execution time. So let's go to the same chip as before. I'm going to take a little portion of this chip. Remember that we have a connectivity limitation in where only adjacent qubits can interact with each other. And we want to execute this quantum circuit over here, where we have the virtual qubits that are from 0 to 4, with the 2 qubit gates that we want to execute. And these dashed lines represent the times in the execution of the circuit. For example, we are going to execute this 2 qubit gate. When it finishes this, you are going to execute the following one, and so on, only one operation at a time. So we are going to start just placing these virtual qubits into the physical one in the hardware in a random way. For example, this one. And we are going to try to start executing the circuit. We can see that the first gate involves the qubit 0 and the 2, but they are not adjacent, so we cannot execute it. The same happened with the following gate. So to fix this problem, we are going to go through the mapping process with several steps. The first one is going to be the initial placement of the qubits, then the routing, and the scheduling of operation. The routing and the scheduling are going to happen at the same time. So let's start the game, but following the steps. Now, this is the other initial placement that we are going to do, but in a more optimal way, not in a random one. So now we are going to start executing and get the algorithm, and we can see that now the first 2 qubit gate can be executed. The second one too, but we can see now that the third one that involves qubit 2 and qubit 4, they are not adjacent, so we cannot execute it. To fix it, we are going through the routing of qubits, and we are going to perform a swap between the qubit 2 and the qubit 0. That is basically an exchange of the position of the qubits. And also we are going to insert the swap in the quantum circuit. So we perform the swap, and we can continue executing all the circuit. Okay, so this is basically the mapping process, and the scheduling of operations. Since this is a very easy example, we cannot see it very well, but it's basically when the gates are going to be executing. If we have a longer circuit, probably with the scheduling of operation, we can prioritize some gates that have more dependencies or perform more operations in parallel and these kind of things. So in summary, what does a compiler in a quantum computing? It receives an input, the quantum circuit, a hardware description, and it will output a circuit that now can be executed in the hardware that we want. So for our servers or end nodes in the quantum network that we are going to use, we are not going to use superconductors. This is because the superconducting qubits has a very short coherence time. And what that means, the coherence time is basically the time that we have a state in a qubit without being corrupted. So when you are executing an application in quantum networks, usually you have to wait a lot of times because you are just exchange information with other servers, and you have to wait a response, and it usually takes time. So the technologies that has been using right now are MV centers. The MV centers are the nitrogen vacancy centers, and they consist on an adjacent nitrogen atom that will substitute a carbon atom and also a lattice vacancy. The good thing about this technology is that it can be manipulated and used in a room temperature, at room temperature by magnetic or electric fields. Also, it can be represented in a more abstract way to understand, in where this purple qubit is the electronic spin of the MV center, and this one behaves at the optical interface. Like we have seen, the servers will have we will make entanglements with another servers to perform quantum communication. So this purple qubit is the responsible one to perform this entanglement. So this is why it's called communication qubit. And with this one, we are also gonna perform the 2-qubit gate. Then we have the orange qubit, that is a nuclear spin, that has longer coherence time than the purple one, and also is better isolated from the electronics, means that if we store the qubit states here, there will be less chances to have errors. This is why it is called memory qubit. So the highlights can be executed at room temperature, and also it has very high coherence time. But not everything is good, because the MV center has a star topology. So what is a topology? A topology represents the connectivity between the different qubits. So the orange ones are the memory qubits, and the purple one is the communication qubit. If we want to perform an operation between different memory qubits, we can't because they are not connected in the graph, basically. So we can see that the memory qubits can only perform operation with the communication one. And this is kind of bad because we only have one communication qubit, which means that if we are performing a communication with another server, we cannot perform any other operations at the same time because this qubit is busy. Not only that, but also we cannot perform several communications simultaneously because we only have one. And when we are performing and also, let's say we want to perform a 2-qubit gate between this qubit over here and this qubit over here. Some of these states should be moved here, then we perform a 2-qubit gate. And then if we want to perform another 2-qubit gate between this and this, these states should be moved again to the other qubit. And then, for example, this state should be moved here. What that means that it's not only that all operations should be done in a sequential way, but also there will be a lot of movements constantly because only one qubit will perform operations. And that means a longer execution time, and also the more operations we perform, the more probability of getting errors and the less fidelity of our execution. Then the other technology that we are using is the ion trap architectures. So basically, the trap ion qubits are implemented using the energy state of atomic carbon, such as carbon, but they can use another atomic ions. There are several of them. And these ions are manipulated using laser to perform gates. Then these ions are arranged and trapped in a 1D linear array via electromagnetic fields. And each ions will store a single qubit. The problem that the single trap has is that it's very difficult to scale. And I forgot to say, MV centers cannot be scalable. So this is another constraint the other technology has. So this one's also in a trap is very difficult because the more ions we have in a trap, the more difficult is to maintain these ions trapped. So one way they have to overcome this problem is, instead of having a lot of ions in just one trap, we're going to have several traps, as we can see here, and we are going to connect the traps via shuttles. This architecture is called QCCD, Quantum Charge Coupled Device. And inside the traps, we have also connectivity. It's not like the superconducting or the MV centers. Like this, if we have a qubit here and another here, it's not necessary to be adjacent or whatever, because all qubits can interact with any other qubits that are in the same trap. But if this qubit wants to interact with this over here, then it has to be swapped into this position to then be shuttled to the other trap. And also, one thing to say is that inside the trap, you can perform operations in parallel, but you are risking to have a lot of errors because of the interferences between the different operations. So usually what it has done is, instead of having operations in parallel in the same trap, you perform operations in parallel, but in different traps. One good thing about this QCCD is that we can have several topologies because our traps connected via shuttles, like this one, or this one, or this one. So just a quick review. We have the ion trap architectures and the MV centers. Good thing about ion trap is that all dual connectivity inside the traps. Since traps have outward connectivity inside single trap, we don't have to perform initial placement of qubit or routing, only scheduling. But when we have this, we have a more complex hardware and more complex mapping procedure. But we will have scalability, and we will have also parallelism. In the MV centers, we have very high coherence time. It can be operated at room temperature, but all operations should be done in a sequential way. We only have one communication qubit, and it's not scalable. So now, the last thing about showing you the background is which frameworks we are using to perform simulations before going to the experiments. So let's say that these are the end nodes. Inside the end nodes, all the gates, qubits, and these kind of things, the interface is defined by the NetQuasar framework. Then each node will have an operating system by the QNode OS. And by NetSquid, we are defining all the physical components of the quantum network, like the routing, the routers, the links, like, for example, latencies, with which kind of links is used, the kind of routers, and so on. And then all of this is inside the Koala framework, where you can orchestrate everything. Now, I'm going to show you what we are doing in my university regarding this. First, we are focusing a lot in the compilation in the SQCCDI or trap architectures. We have already done an initial placement for this kind of topologies. Well, it works for everything, for every topology, but we have used this one for the experiments. So for this initial placement, we use a qubit interaction graph where the nodes represent qubits and nets the interaction between the qubits. For example, 0 and 2 have 3 gates in common, so the weight of the edge is a 3. Here we have an example of a quantum circuit, and again, the dashed lines represents the operation that can be executed at a specific time. So these two operations can be done in parallel, then this one, then these two, and so on. The things that we have considered for our algorithm, that is called spatiotemporal hour qubit mapping algorithm, is first the number of times qubits are involved in the same operation. Like I said here, for example, 3 times the 0 and 2, 2 times the 3 and 1, and we consider it to place them in the same trap. Also, we have considered a specific qubit with how many other different qubits it interacts. For example, the qubit number 2, it interacts with literally all the other qubits. So it will be very important in where to position this trap to try to reduce the shuttles and the swaps. Because here we have 2 traps, but let's say imagine we have here another trap. If we place the 2 here in this position, we know that it's going to interact with all qubits, so it will have probably to be moved a lot through the device. But if we place it in the middle, the number of swaps and shuttles will be minimal if you compare it in the other part. And the other thing we consider is also when the operations take place, because this is an initial placement, not a routing. So for us, it's more important the operation that takes earlier in the execution of the circuit than at the end, because at the end, through the routing, all the qubits will be already moved. So it doesn't have the same weight at the ones that are in the beginning. And the last thing is the excess capacity. And what that means, when we have all the imagine that we have all spaces of the traps busy by qubits. Then we will have a problem because we cannot move one qubit to the another trap because it's already full. So the excess capacity means the free spots that we have in the trap. So for example, here we have one free spot, and we have to decide if we move the 0 here or the 4 here. So it will be better to put the 4 here because then we don't make the trap full. These are the results. I'm going to go very quickly about it. And we compare it with a random algorithm and with a greedy one that is already being used. And this is the how much better our algorithm algorithm is regarding execution time, comparing with the greedy one and with the random one. We can see that for a structured algorithm, the cooker adder, dropper adder, QAOA, and QFT, we have very good results, but with the random ones, that is, quantum volume has a very important random component and random algorithm, the improvement is not that high because we cannot predict very well how the algorithm will behave. Doing the research, we also have seen that I'm not showing the results because I'm not having time, but we have seen that the parallelism is going to take a very important step. But we have to consider something. If we want to increase the parallelism of the execution of the operation, we're also going to increment the number of shuttles because we are trying to distribute more the ions through the different traps. So then there is a trade-off, like, okay, what is better? To do more parallelism and have more shuttles and swap, or do it in a more sequential way, taking more time, but reducing the number of movements? So this is the next work we have done. First, we have performed an experiment where we create a benchmarks in where all qubits are involved in 2 qubit gates at every time of the execution of the circuit. So all the time, all qubits are executing in a parallel way. And also there, we can control the percentage of movements. That means that 100% movement is after a 2 qubit gate that has been performed with a couple of qubits, that qubits are going to move to another trap with all of them. So all qubits moving after the operations. And 0% is there is absolutely no movement through the different traps. So we have seen that for 20 virtual qubits, the red dots and the red crosses here will mean a sequential execution, comparing with the parallel one that is the other data. And here is the fidelity. Movements at T2 is the different coherence range. But the more important is the fidelity and then movements. We see that for 20 virtual qubits, well, it's almost, the parallel thing doesn't mean anything. It's almost better doing it in a sequential way. But in the moment that we increase to 40 virtual qubits, we can see that with 20% or less movements, it's better to perform in a parallel way, even though we increase the number of shuttles and movements. But another thing to take into consideration is that here we are working with random algorithm, which means that we cannot predict movement. So the next thing we have done is to do the same, but with some structured algorithms to see the behavior. Here we have the fidelity and here the number of traps, because there is no routing algorithm that tries to do parallelization right now. So we have forced this parallelization by increasing the number of traps and reducing the ions per trap. For example, with 20 virtual qubits and 2 traps, it's going to be 10 qubits in one trap and 10 in another trap. So only 2 operations in a parallel way. But with 10 traps, you are going to have 2 qubits per trap. So we can have up to 10 operations in parallel, but we will have a lot of more movements and swaps. We see again that for 20 virtual qubits, only for the Cucaro adder is worth it to do it in a parallel way. But then when we increase to 40 virtual qubits, there are some instances that behaves better with some degree of parallelization. And you can see it better in this table over here, where we have 20, 40, and 50 virtual qubits. Here, this is the optimal number of traps that behaves, that is where we have the best results. Maximum number of traps means up to how many number of traps we have better results than in a sequential way. And the gain of fidelity for the optimal number of traps comparing with a sequential execution. For 20 virtual qubits, okay, the increasing of the fidelity is not that good, so we can ignore it. But then we increase to 40 virtual qubits, the optimal number of traps improves, also the maximum number of traps increase, and we can see a very interesting gaining of fidelity. And then for 50 virtual qubits, okay, the fidelity it's impressive, the number of fidelity that we can increase. So this is telling us that in the future, with more qubits in the devices and more traps, the most important thing, or one, not the most, or maybe I don't know, but one of the most important things will be to consider the parallelism. So what I'm working now is in a routing mapping algorithm that considers all of these things of the parallelism. And the last thing we are working on is in simulate a full stack execution of the quantum internet. That, if you remember, we have this Scala framework that involves all these components. So what we are doing is, with the Scala framework, we are going to simulate the different applications execution by varying some parameters, such as number of routers, numbers of servers, number of qubits per serve, also varying the number of communication qubits, memory qubits, and so on, and also for different technologies. So in this way, we can check which technology is more optimal as the other for which application, because maybe, I don't know, for QKD will be better NV centers, but maybe for quantum distribution is better